In 2015, Typhoon Soudelor struck Taiwan with sustained winds of more than 107 miles per hour. Inside Taipei 101, once the tallest building in the world, a 728-ton steel sphere began to swing. What can look like a malfunction is actually one of the systems that helps keep the building's motion within safe limits, a tuned mass damper. And once you understand why it works, you will never look at a skyscraper the same way again. Skyscrapers are not rigid, they are designed to flex. Historical Empire State Building materials state that in a 110-mile-per-hour wind, the building sways about 1.48 inches. The Burj Khalifa, by contrast, can sway up to 5 feet in either direction in high winds. That movement is not a structural defect. It is a deliberate engineering choice. A tall building that cannot flex simply concentrates stress until something cracks. The real problem is not movement by itself. The problem begins when external forcing pushes a structure near one of its natural frequencies. Every object has a natural frequency, the rate at which it prefers to oscillate when disturbed. And when a repeating force arrives at or near that frequency, the response can grow dramatically. That is resonance. In 1940, the Tacoma Narrows Bridge in Washington state entered a destructive oscillation in winds of roughly 40 miles per hour. It collapsed due to aeroelastic flutter caused by wind-induced oscillations, exacerbated by its aerodynamically unstable design and lack of sufficient stiffness and damping. The Tacoma Narrows was a suspension bridge with a span of about 2,800 feet. It was destroyed by wind at exactly the wrong frequency. So the problem tall buildings must solve is the dynamic response wind can trigger. If a tower's motion is allowed to build unchecked, occupants feel it. Non-structural systems suffer, and in the worst case, the structural demand itself can become dangerous. The engineering solution to a swaying building is to place another object inside it that also sways, but in the opposite direction. A tuned mass damper is a large weight suspended from cables or mounted on hydraulic bearings near the top of a structure. It is mechanically tuned to oscillate at the same natural frequency as the building. When the building moves in one direction, the damper moves in the other. The two forces partially cancel. The net result is a structure that moves significantly less than it otherwise would. This principle is called destructive interference, the same principle that makes noise-canceling headphones work. You apply an equal and opposite force, and the two signals annihilate each other. The damper inside Taipei 101 is the most visible example of this technology. The sphere weighs about 728 US tons and hangs on 8 steel cables between the 87th and 92nd floors. During Typhoon Soudelor, it moved roughly 3.3 feet, counteracting what would otherwise have been significant structural oscillation. Taipei 101 also made a deliberate architectural decision to put this engineering on display. Visitors can see the system rather than having it hidden behind walls. That turns a piece of structural engineering into part of the public experience of the building. A rare case where the mechanism that keeps the structure comfortable is also one of its most memorable interior spaces. But not every case of structural instability is as transparent. In 1978, 1 year after the Citigroup Centre Tower in Manhattan opened, a structural engineer named William Le Mesurier received a phone call from a student. The student had noticed something unusual about the building's column placement and wanted to discuss it for a class project. Le Mesurier began reviewing the original calculations. What he found was not a theoretical concern. The building had been designed to withstand perpendicular winds hitting its flat faces directly. The quartering winds striking the building at 45 degrees, had not been properly accounted for in the final construction. The joints connecting the building's structural members had been changed during construction from welded to bolted, a modification approved at the time, but not re-evaluated against the full range of wind conditions. When Le Mesurier ran the corrected numbers, He found that a storm capable of occurring roughly once every 16 years could cause the building to fail. In Midtown Manhattan, a 59-story tower, housing a Citibank branch, offices, and a church at its base, St. Peter's, which had been promised its building would never be demolished. The remediation was carried out at night. Steel plates were welded over the vulnerable joints after business hours. Emergency evacuation plans were drawn up for an 11-block radius. The work took several months. The building's tuned mass damper was part of the original design, but the defect meant that if the damper lost power in the event of a major storm, the structure's safety margin fell further still. The public did not learn of the incident until 1995, when the New Yorker published an account. By then, the building was safe, but for several months in 1978, it was not. The tuned mass damper is just one expression of a broader engineering idea. Use a system's own dynamic behavior against itself. The goal is not to make every structure perfectly rigid, but to keep vibration, displacement, and acceleration within acceptable limits. You can find the same idea well outside skyscrapers. In automobiles, mass dampers are used to reduce vibrations transmitted from the road or powertrain into the chassis and to suppress resonances in large panels such as roofs, doors, and tailgates. In bridges, tuned mass dampers are installed to fight wind, traffic, pedestrian, and even earthquake-induced vibration. In spacecraft and launch vehicle work, NASA has described tuned mass damper-based approaches for dealing with dangerous resonance problems, even though mass and packaging constraints often force engineers to adapt the concept for their vehicles. The mass damper approach requires knowing precisely what you are designing against. A tuned mass damper that is calibrated incorrectly for the wrong frequency or the wrong amplitude can in principle make oscillations worse. The tuning is not incidental. It is the entire problem. Engineers use wind tunnel testing, finite element analysis, and decades of accumulated data from instrumented buildings to get that tuning right. The sphere in Taipei 101 arrived at 728 tons after calculating the answer to a specific question. What mass, oscillating at this frequency, will reduce the building's peak displacement by the required margin? The next time you are in a tall building on a windy day, pay attention. If the building feels entirely still, that is not because nothing is happening. It may be because something is working correctly. A large mass, somewhere above you, quietly swinging in the other direction. That slight sense of unease you might feel on a high floor in a strong wind is not irrational. Buildings do move. The engineering goal is not to prevent that movement entirely. It is to keep it within limits that the structure and the people inside it can tolerate, which, if you think about it, is a reasonable summary of most structural engineering. If this is the level of depth you want from engineering content, subscribe to Engineering Manual.